Lesson 3 is a review of transformations from pre-Cal 12 and how we make new functions from old functions. So in pre-Cal 12, you had the standard form of a transformed function and it looked like this. Y equals negative a and you multiplied by your generic function, bracket, plus or minus b. I'm just going to leave it as negative here for now. Bracket x minus h plus k. And in this generic equation, each of the parts a, b, h, and k made a transformation to the graph. The negative out front and the negative in front of this coefficient here also determined if it was going to be reflected upside down or backward. So when we are looking at a function plus c, in our generic equation, this is my plus k bit. Okay, this represents a vertical shift c units up. So if it's a plus c, we are moving up c units. If we saw a negative c, we were moving down c units. When we are looking at the transformations to the x, though, if the c is next to the x on the inside of the bracket, we go in the direction opposite what we see. So here I see x minus c, so that's a positive shift. That means I'm going in the positive direction, right, c units. Similarly, if I see that it is positive, I am flipping the sign and going back or to the left, c units. And the reason that the x's are backward or the opposite sign than the y's is really because if we were doing an honest transformation, we would be replacing y with y minus k, and we're replacing x with x minus h. So I would have something like y minus k equals f of x minus h. And if we wrote it like this, then both of them would have an inverse sign. This would be moving up k units, and this would be moving right k units. But because we write our functions in y equals form, if I wrote it as y equals form, to get this k over to the other side, I have to add k to both sides. So I can't change what's happening to my x, but I can move the k over here. And because of that sign change, that's why whatever we see in the k place is the shift that we see. So if it ends up being positive, we're moving up. And if it ends up being negative, we're moving down. Okay, so rule of thumb, when we are looking at this generic form, whatever is happening to the outside of the equation, so this and this are transformations to the y. The plus k is shifting it up or down depending on if that's positive, negative. And the a is expanding it, which I'm going to get to in the next section here. So this is just a review of transformations. So if I had a generic function such as f of x equals the square root of x, remember some of our key points in the previous lesson that we did square root of x. So we do 0, 1, 4, 9. We always pick numbers that we can actually take the square root of. This would be 0, 1, 2, 3. So when I draw this, 0, 1, 2, 3. Oh, I think my 9 is a little bit off the charts here. 4, 8. Yeah, so the 3 would actually be out here. That's okay. I just want the general shape. So that's my f of x. Now, if I take my f of x and make a new function, g of x, and all I've done is take my original function and add 2, then my transformed function is going up 2. That means 1, 4, 9. 0 plus 2 is 2. 1 plus 2 is 3. 2 plus 2 is 4. 3 plus 2 is 5. So all of my y values are getting shifted up 2. Boom, boom, boom. Oops, I put this one in the wrong spot here. Oh, my pen and eraser are not working together. So up 2, up 2, up 2. There is my transformed function. I've raised the function by 2 points. I haven't done anything to the x because it's still square root x, but I've added 2. Now, if I do my h transformation, I have new points. I am moving my x to the right 3 points, and I am moving my graph down 1 point. Now, here's where we have to be a little bit careful. I cannot now use x equals 0 because 0 minus 3 is negative 3, and I can't take a square root of a negative. So I have to start at a number that would make this 0. So then to make this 0, my starting point is 3, which makes sense. I've taken my 0 and I've moved it to the right 3. So I'm going to add 3 to all of these numbers here. So it's going to be 3, 4, 7, 12. Now my y has been shifted down 1. So 3 minus 3 is 0. 0 minus 1 is negative 1. 4 minus 3 is 1. 1 minus 1 is 0. And so on. So you can see from my original function, all my y values are going to be shifted down 1. 1 and 2. So now I have something that is shifted to the right 3 and down 1. So here, here, and then 7, let's see, this is 3, 4, 5, 6, 7 is at 1. So there is my new function. So for the red line, I have taken my x and y values from the original function. So any x and y values in f of x graph, I have transformed in the red function as leave the x's alone, take the y's, and add 2. I've shifted them up 2. For the green graph, I have taken the x values, moved them to the right 3, and moved them down 1. When we are talking about reflections, putting a negative next to the x means we are reflecting about the y-axis. Now remember, the y-axis is a vertical line, so this is a reflection backward. That means I'm taking my base function, whatever the coordinates are, and I'm reflecting them about the y-axis. I'm replacing x with negative x, and I leave y alone. If I have a transformation where I am replacing y with negative y, meaning I'm taking my whole function and I'm making it negative, now I am reflecting it upside down over the x-axis. So I'm taking my base function points, x, y, and I'm transforming them to leave the x alone, make the y's negative. And then we have a special case here. We talked a little bit about this in the last lesson. This is an inverse function. Means instead of y equals, I have x equals, and I know my y. This is a special case. I'm going to change my color here to blue, where we are reflecting over the diagonal line. So you want to fold your graph paper in half on that blue diagonal that I just drew. Okay, so now I'm taking my original coordinates x, y, and I'm transforming them to y, x. So whatever numbers I had in x, y, I'm flipping the order when I do the inverse. Okay, so let's see what an example graph looks like. I'm going to erase the imaginary lines that I just drew on the graph. So this is diagonal. I don't think I spelled that right, but you know what, mathlete, not English teacher, so let's just leave it at that. You heard what I said, diagonal line. X equals y is the diagonal line. So let's erase all these. Let's take a look at what these functions look like. So I'm going to look at this 2 to the power x. We just did this in our last lesson, right? When x is 0, my function has an intercept of 1. When x is a big positive number, it's going to grow exponentially. When x is a negative number, it's going to get smaller exponentially. And I have an asymptote on the x-axis. That's my base function. Now, looking at g of x, I put the negative next to the x. That means I'm flipping it backwards. That means I'm flipping it over the y-axis. So this point's not going to change. If I flip it backwards, that means it's going down and to the right, up and to the left. If I put my negative on the outside of the function, make the whole thing negative, that means I'm flipping it upside down. Remember, the black line is my original. So if I flip it upside down, my intercept now is at -1. I'm going down and to the right, up and to the left. So it is upside down. If I'm doing the inverse, remember the inverse of an exponential is a log function. So, and again, we kind of drew this in the last lesson. So here's my diagonal line essentially. Now my intercept, I'm going on the kitty corner, right? Diagonal corner. It's a 0, 1 here. Now it's 1, 0. And if I flip this upside down, I'm going to get something like this and like this. Actually, sorry, it's not going to cross the y-axis. Let me draw a better line. There we go. So this is flipped over on the diagonal. So you can see the 3 types of reflections that we can do. Okay, so where we put the negative matters in terms of is it backwards or is it upside down. In order to flip it, excuse me, in order to flip it on the diagonal, we are exchanging the positions of x and y and resolving for y. Okay, let's move on to our next page here. All right, the next thing that we learned in Pre-Cal 12 is to do stretches and compressions. So if C is a positive number greater than 1, so we are multiplying the function by C, we are stretching it vertically by C, and we call this an expansion. It's getting bigger. If we are replacing if we are putting a coefficient less than 1, so it's 1 over something, this would be a compression. And also I should specify, so this is getting smaller, both of these are vertical. Vertical compression, vertical expansion. Okay, now again, when we put the C in the X, this is a compression by C, or again, I'm just going to use a different color here to make sure we are identifying. This is horizontal. I'm just going to use an H. I don't want to spell out the whole word. And we're doing the inverse. This is a compression. That means it's getting smaller, and we are multiplying it by a factor of 1 over C. And here, because it is already 1 over C, we are looking at an expansion. So we're multiplying by C. Okay, so again, if we're thinking of the mapping coordinates, if my original coordinates are x, y, then to go here, this would be x C times Y. This one would be X, Y over C because it's in the denominator. However, here it would be X over C, leave the Y alone. And for this one, it would be C times X, leave the Y alone. Okay, so the X's are always the opposite of what you see. The Y's, you're just doing what you see in the coefficient. Okay, so again, let's take a look at a base function. Let me draw in some points here. Let's say this is 1 and this is -1. Since we're doing trig here, let's say this is pi by 2, pi, 3 pi by 2, 2 pi. Let me make it really clear. Okay, so sine function starts at 0, goes up to 1, down to 0, -1, back to 0. I'm just going to do one rotation and I'll just keep it positive just to keep things simple. Okay, if I put a 2 inside the bracket next to the x, that means I am halving the x. I'm squeezing it by 1/2. So my compression here getting smaller by c. Instead of going from 0 to 2 pi, I'm going to go from 0 to pi. That means this pi by 2 is my halfway point. That means here are my peaks of the graph. There it is. I've squeezed it in by 1/2. If I have a 3 on the outside, that means my x's aren't changing, but I am changing the y values to 3 times. Ooh, I see my mistake here. I should have made the 1 a little bit lower. But if this is 1, then this is 2, and this is 3. And then this is 2, and this is 3. So now I'm stretching it vertically and then going down, right? So my y values, the peaks of my y values will be at +3 and -3. My x values stay the same. So that's a vertical stretch by 3 for this one. So that's h of x is in pink, g of x is in green. And if I do the last example here, j of x, I'm going to do it in blue. I see a 1/2. It is on the outside of my function, so therefore this is a vertical, and because it's a 1/2, it's a vertical compression. So I'm taking my values at 1, the peaks, and I'm bringing them down by 1/2, down by 1/2. So my wave is shallower, but my x's are unchanged. So that's a review on the stretches and compressions. So in the last little bit here, I'm going to do some examples of combining transformations. I'm going to use a mapping notation in order to help us. The base function here for question 1 is y equals root x. So what have I done? I've done a whole bunch of things. There's a -2. Negative means I flipped it upside down. 2 on the outside means I have a stretch by 2. So I've made it taller by 2. Then I have a +3 on the inside of the root. Remember, with x's, we flip the sign. So that means I'm going left 3. And I have a -1 on the outside. I'm going down 1. So that's lots of information there. So I'm taking my base points, x, y, and I'm transforming them to the x is being moved over to the left by 3. The y, I am multiplying by -2, and then I'm shifting it down by 1. So remember the key points that we just did on the previous page. 0, 0, 1, 1, 1, 2, 3, 4, 2. So this is the shape of my base graph. What happens to it now? I'm going to take my x. I'm going to move it 3 over. Oh, actually, my bad. I got to follow BEDMAS. When we follow BEDMAS, we have to do any kind of, oh my goodness, my spelling. We have to do any kind of multiplication stuff first. So actually, because there's a -2 here multiplying my y, I actually have to flip it first. So I'm going to flip it upside down because I'm making my y negative. I also have to stretch it, make it taller by 2. So I need to take my points, multiply them by 2. So I'm going to make it taller. Now I can move it left and right. I'm going to take all my points and move them left 3, down 1. So my final graph is going to look like this. 1, 2, 3, 1. 1, 2, 3, 1. 1, 2, 3, 1. Here is my graph. So the black is the original, the red is the final, and the blue is just me mapping it out. All right. All right, in the second example, what's my base function here? I see an x in the denominator. That tells me this is a rational function or a reciprocal function. That's my base graph. Now, on the base graph, remembering from our first lesson, it essentially looks like this. My key points are 1, 1, and -1, -1, with the asymptotes at the origins. So y equals 0, x equals 0 are my vertical and horizontal asymptotes. What am I doing here in terms of transformation? I see a 2 next to the x. So that tells me I have a horizontal compression by 1/2. So I'm squeezing it in. I have a shift to the right, the left by 1, and I'm shifting it up 2. There are no negatives here, so I don't need to worry about a flip. So this one's going to be a little tricky to see because, well, here, I'll zoom in. But we are moving this in by 1/2, squeezing it in. Then we are moving our key points left 1 up 2. So left 1 up 2. Here's my new point. Left 1 up 2. Here's my new point. So my little thingies are going like this. My vertical and horizontal asymptotes also move with the graph. Fun facts: when you do compressions and reflections, they do not affect the asymptotes. However, when you do translations, left, right, up, and down, it does affect the asymptotes, right? So if my original asymptotes were here, they are now shifted with the graph here. So my vertical asymptote is at x equals -1 because I moved to the left 1. My horizontal asymptote has now moved to y equals +2. A really nice way to see where your asymptotes are is look at where your translations are, left, right, up, and down. So black graph compared to pink graph, original versus translation. You can also think of it in mapping notation. If my original point's x, y, what did I do to them? Well, I have a 2 next to the x there, so I have compressed my x by 2, and I have shifted it to the left by 1. Nothing has happened to the y other than putting it up by 2. So those are my mapped coordinates. So you can use any coordinates to map it. If you know some key coordinates, key points, that makes life a whole lot simpler. All right, everybody's favorite trig examples. Hooray. All right, first I'm going to start with the base graph. Let me choose a correct height though. I see a vertical expansion by 3, so I need to get to at least 3 at some point, and I'm going to go to a -1. 1, 2, 3, 4, 5, 6. Okay, I think I'm just gonna, it's gonna be a bit of a squeeze, but I'm just going to make each box worth 1 on the vertical so that you can see all the different transformations. And then when I do my horizontal stuff, I'm going to stick with what I had. Let's call this pi by 2 and pi, 3 pi by 2, 2 pi, and the same going in the opposite direction. So first I start with my base function. I know my base function is sine x. So sine x starts at 0, moves up, back to 0, down to 1. Ooh, I just made the mistake here that I was trying to avoid. We said that each square is going to be worth 1. So this is going to be a little awkward looking, but that's all right. Here is my base function, sine x. Okay, what am I doing here? I'm taking my values, x, y, and how am I transforming them? I see a 2 next to the x. I don't like it the way that it is. I want the coefficient on x to be positive 1. So what I'm going to do here is I'm going to factor out the 2. That's going to be x plus pi by 2. You always want to have a factor on here, okay? And then all the stuff on the outside stays where it is, no problems there. Okay, so the 2 tells me I have a horizontal compression by 2, so I'm squeezing it in, and I'm shifting it to the left pi by 2. The outside numbers tell me I am flipping it and stretching it by 3 and then shifting it down 1. So my x values are getting divided by 2, and we are minusing pi by 2. For my y values, we are multiplying them by negative 3y and then shifting them down by 1. All right, this is going to be a little bit tricky, but we are confident and strong and we can do it. Okay, so we need to do the multiplication bits first. So I got a half the x's and I have to negative 3 the y's. So half the x's means I'm going to go here, here, and here. So I'm going to go up, middle, down. Okay, so that's half my x's. And then I'm going to flip my graph. So I'm going down here. There we go. So now it's upside down. That's the negative on the y. And then to make it times 3, I have to go 1 times 3 here, 1 times 1, 2, 3 here, 1, 2, 3. So I've made it taller by 3. Okay, and I'm going to use another color to do the next bit so that we're not getting confused here. Okay, so the pink means I've divided the x's by 2, I've compressed it. The blue is me flipping it over and making it taller by 3. So now what's left is the horizontal and vertical shifts. I'm moving it left pi by 2. So my starting point is going to be here. That's my pi by 2. And I'm moving it down 1. Okay, so here, here, here. Nope, I did not move it down 1 at the point here. It's going to be down 1. Okay, this, oh, getting tricky now. Positive 2 and back down. There we go. Okay, I'm going to zoom in here. Okay, I'm trying to make that a little bit smoother so you can see. I'm going to erase that. There we go. Okay, so the green is my final graph. Let's double check it. I have an amplitude of 3. 1, 2, 3. Done. It is going down. So here's the start of my graph, right? In the black, the start of my graph started at 0, went to 1 here, and then came down to pi by 2. So you can see, because I've flipped it upside down, it's starting and going down instead of going up. down to 3, back to the midline, up by 3, back to the midline, which should actually just be right there. Okay, so we want an amplitude of 3. It is shifted over by pi by 2. We said that 2 squares is pi by 2, but we're moving it left. So my starting point is here at negative pi by 2. And we've shifted it down 1. So it's off of the x-axis down 1. So we did that correctly. All right. That's probably the most complicated one that I can think of to do without being totally mean. So this is just, again, an all-in-one example of what we do when we have translations. We still have to follow BEDMAS. So reflections and compressions come first, then we shift our final product to where we need it to be. Okay? Sometimes we are going to get equations that are not in the form that we would like. So remember on day 1 when I said we are going to practice having to do vertex form. And the reason we do vertex form is vertex forms tells us very easily where all the shifts are. So here I have a quadratic equation, but it is not in the form that I need it to be. So I got to do some math here. I'm going to factor out the negative 3. So I end up with x squared plus 2x. Oh, actually, no. I'm going to complete the square. Well, let's complete the square in a second here. First, let's factor. We're going to get a 2x plus minus 8 over 3 because it doesn't factor very nicely. Okay, and then to complete the square, I'm going to do a negative 3 x plus 1 squared minus 1 squared minus 8 over 3. And then I'm going to collect these two terms. I'm going to distribute the 3 here. So this is going to be negative 3 x plus 1 all squared. Negative 3 times negative 1 is going to be positive 3. Negative 3 times negative 8 over 3 is going to be positive 8. So 3 plus 8 is going to give me 11. So you can see why we focus on vertex form. Look at how beautiful that looks. I know this is a quadratic. I know the shift is a vertical 11. I know it's upside down, stretched by 3. And I know it is moved to the left by 1. So what's a base function? Y equals x squared looks something like this. So I do my compressions and reflections first. It is now upside down, and instead of 1, 1, it's going to be 1, 3, 1, 3. So that's my reflection and my stretch. But then I have to move it left 1, right? And then I have to move it up 11, so it's going to be somewhere up there. It's going to look something like that. All right. So sometimes we're going to be given an equation and we just got to fix it for a bit to make it in a form that fits the standard form of how we do transformations. And if we have a quadratic, that form is always going to be vertex form. All right. Now, absolute values. I think I'm going to actually save this for our next lesson because it's going to talk a little bit more about domain and range. So I'm going to make that into its own section. All right, that's it for today.